Before we get into what Webb actually found, if you're someone who loves exploring the depths of space, spend a moment hitting the thumbs up or subscribe to the channel. It helps more people find this kind of content, and it means a lot. Now back to Alpha Centauri. Let's start with something familiar. Look up at the night sky from the southern hemisphere on a clear evening, and you'll find a bright star low on the horizon in the constellation Centaurus. It doesn't look special, it's just a point of light. Steady, brilliant, easy to miss if you don't know what you're looking for. But that star, or rather, that cluster of stars, is Alpha Centauri, our nearest stellar neighbor, the closest star system to our own sun. And at a distance of about 4.37 light-years, it is also one of the most studied and celebrated objects in all of astronomy. Not because of what we've found there, because of what we've always imagined might be there. Alpha Centauri is actually 3 stars, not 1. 3. The 2 brightest, Alpha Centauri A and Alpha Centauri B, orbit each other in a slow gravitational dance that takes roughly 79 years to complete. They're close enough that from a great distance they appear as a single brilliant point. But they're 2 distinct suns. Alpha Centauri A is slightly larger and brighter than our own sun. Alpha Centauri B is a little smaller and dimmer. Both are G-type and K-type main sequence stars. Both are middle-aged, stable, hydrogen-burning stars. They're the most sun-like stars anywhere in the sky. Think about that. Of all the hundreds of billions of stars in the Milky Way, the ones most similar to our own sun happen to be right next door. The 3rd member of the system is Proxima Centauri. It's a red dwarf, much smaller and cooler than the other 2. It orbits the AB pair at an enormous distance, roughly 13,000 astronomical units out. That's so far that it takes Proxima Centauri somewhere around 500,000 years to complete one orbit around its 2 companions. Proxima doesn't glow the way A and B do. It's far too dim to see with the naked eye. But Proxima holds a special distinction. It's technically the closest individual star to our sun, not Alpha Centauri A or B. Proxima, by a small margin. At about 4.24 light-years away, it edges out its companions by a fraction. Now, 4.37 light-years might not sound like much. It's a number, you can say it in half a second. But let's put it in perspective. Light travels at about 186,000 miles per second. In 1 year, it covers roughly 5.88 trillion miles. Multiply that by 4.37. The distance to Alpha Centauri is about 25 trillion miles. Our fastest spacecraft ever launched, the Parker Solar Probe, can reach speeds near 430,000 miles per hour under the right conditions. At that speed, the trip to Alpha Centauri would take roughly 6,300 years. Not decades, not centuries, thousands of years. We launched Voyager 1 in 1977. It's been traveling for nearly 50 years. It hasn't covered even a fifth of a single light year. That's how far away 4.37 light-years actually is. And yet in cosmic terms, Alpha Centauri is essentially our backyard. The Milky Way is about 100,000 light-years across. The nearest major galaxy, Andromeda, is roughly 2.5 million light-years away. Compared to those distances, Alpha Centauri is so close it's almost touching. It's the astronomical equivalent of a neighbor whose front door you can almost see from yours, except that walking there would take 6,000 years, close and impossibly far at the same time. This is part of why the system has held such a grip on the human imagination. It's the nearest destination, the first waypoint on any map of the galaxy we might ever try to draw. In 2009, the movie Avatar placed its story on a moon orbiting a gas giant around Alpha Centauri A. The filmmakers chose it for a reason. It's the obvious answer if someone asks you to point at the place humans might go first. Science fiction has visited Alpha Centauri dozens of times. Books, films, games, thought experiments. The system has stood in for hope and ambition, and the idea that we might one day not be confined to this single solar system. That pull is real. It's not just fantasy. Astronomers genuinely regard Alpha Centauri as the most important nearby target in the search for other worlds. And the sun-like nature of Alpha Centauri A matters more than almost anything else. When we search for planets that might support life, we tend to look near stars like our own. Stars with similar temperatures, similar ages, similar brightness. Alpha Centauri A fits that description almost perfectly. It's close to the Sun in mass, in luminosity, in surface temperature. If there's a planet orbiting Alpha Centauri A at a distance anything like the Earth-Sun distance, it would receive roughly similar amounts of starlight. It would exist in conditions that aren't wildly alien to us. That possibility, however uncertain, is why the system commands so much scientific attention. It's the closest place in the universe where something recognizable might exist. For as long as humans have dreamed about leaving the solar system, Alpha Centauri has been the destination. Date. Here's the strange thing about Alpha Centauri. It's the closest star system to Earth. It's been in our sky for as long as humans have looked up. Astronomers have pointed telescopes at it for centuries. And yet, until very recently, we had almost no idea whether it had any planets at all. That's not an oversight. It's not a matter of nobody bothering to look. The problem runs deeper than that. Alpha Centauri is so close, and the stars in it are so bright, that studying the space around them for planets is almost impossibly hard. The very thing that makes this system special, its proximity, is also what makes it a nightmare to work with. Think about what brightness means for a telescope. When you point an instrument at a very bright star, the light from that star doesn't just illuminate the star's location on your detector. It bleeds outward, it scatters. It creates halos and spikes and ripple patterns across the surrounding image. Anything faint sitting near that star gets buried under all that noise. A planet orbiting close to a bright star might be 10,000 times dimmer than the star itself. From the telescope's perspective, trying to pick out that planet is like trying to spot a firefly sitting next to a floodlight. The firefly is there, you just can't see it. Alpha Centauri A is almost identical to the Sun in temperature and luminosity. Alpha Centauri B is slightly smaller and cooler, but still a brilliant star. Both of them are extraordinarily bright objects by the standards of what telescopes have to deal with, and they're not far apart in the sky. From Earth, the two stars appear separated by only a few arcseconds at most, a tiny fraction of the width of the full moon. So when you point a telescope at Alpha Centauri A, Alpha Centauri B is essentially right there next to it, flooding the surrounding image with its own light. Ground-based telescopes face an additional problem on top of all that. Earth's atmosphere is constantly moving. Pockets of warm and cool air shift and churn above every observatory on the planet. That motion bends and blurs starlight continuously. On a good night at a good site, a ground-based telescope can resolve fine detail. But it's never perfect. The atmosphere smears things. Stars that should appear as sharp points instead shimmer and spread. That spreading makes it even harder to distinguish a faint planet from the glow of the star it orbits. For most of telescope history, there was simply no technology capable of overcoming both of those obstacles at once, the blinding brightness of the stars and the blurring of the atmosphere, well enough to even begin searching for planets around Alpha Centauri A or B. Hubble changed part of that. Hubble sits above the atmosphere entirely, so the blurring problem goes away. In space, stars are sharp points. Hubble could resolve Alpha Centauri A and B as two separate objects, which ground-based images of the system often couldn't do clearly at all. That was a genuine step forward, but Hubble still couldn't do what actually needed to be done. It wasn't built for this kind of work. Its instruments weren't designed to suppress the glare of a bright nearby star well enough to hunt for planets in the immediate vicinity. Hubble could see the two stars. It couldn't see what might be orbiting them. In 2019, astronomers tried something more ambitious. A team used the Very Large Telescope in Chile, one of the most powerful ground-based observatories ever built, as part of an experiment called NEAR, which stood for New Earths in the Alpha Centauri region. The goal was to look for planets around Alpha Centauri A and B using a specially modified instrument designed to block stellar glare. They used a coronagraph, a device that physically masks the star's disk to reduce the blinding light, combined with adaptive optic systems that correct for atmospheric distortion in real time. The results were tantalizing. The team found a faint signal, something in the vicinity of Alpha Centauri A that didn't obviously belong to the star itself. They labeled it a candidate. They published it carefully with extensive caveats. The detection was tentative. It could have been a real planet. It could have been an artifact of the instrument, a spurious signal produced by the complex light patterns around the star, rather than by any actual object. They couldn't confirm it. They couldn't rule it out. That ambiguity sat there for years. A possible planet around the nearest sun-like star, hinted at by one instrument one time, impossible to verify. The problem wasn't just technical. It was fundamental to what these stars are. They're too bright. They're too close together in the sky. They move quickly across the sky relative to the background of distant stars, which limits how long any single observation can run. Every factor that makes Alpha Centauri the most accessible star system in the universe conspires to make it one of the most difficult targets for planet hunting that exists. We had been staring at those stars for centuries. We had named them, cataloged them, measured their properties in extraordinary detail. We knew their temperatures, their ages, their masses, their chemical compositions. We knew how they orbit each other. We knew their distance from Earth to within a fraction of a percent, and still we couldn't say whether there was a single planet anywhere around them. What was needed was an instrument that could block stellar glare more completely than anything ever built before, operate above the atmosphere entirely, and detect objects tens of thousands of times fainter than the stars themselves. All of that changed in August of 2024. Getting a clean look at Alpha Centauri A with any telescope is a technical nightmare. The star is brilliant. It's one of the brightest stars in the entire sky. And when you point a telescope at something that bright, the light doesn't just sit neatly in one spot. It bleeds, it scatters. It reflects off the inside of the instrument and creates ripples and rings and spoke-like patterns that spread across the image like noise on a bad signal. Any planet orbiting Alpha Centauri A would be sitting somewhere inside that glare, drowned out, invisible, a candle next to a spotlight. To deal with that, astronomers use a device called a coronagraph. The basic idea is simple. You place a small physical mask inside the telescope that blocks the star's light directly, the same way you might hold your hand up to block the sun on a bright afternoon. Block the source, and suddenly the space around it becomes visible. That's the concept. The reality is considerably harder. When you block a star with a coronagraph mask, you don't get a clean, dark circle. The light bends around the edges of the mask. It interferes with itself. It produces concentric rings of brightness radiating outward from where the star was, and spoke-like streaks extending through the image in multiple directions. These are called diffraction patterns. They're a consequence of physics. You cannot eliminate them entirely. You can only try to understand them well enough to subtract them out mathematically after the fact. That alone is a serious problem. But Alpha Centauri makes it worse. Alpha Centauri A doesn't sit alone in the sky. Its companion, Alpha Centauri B, is right there next to it. From Earth's perspective, the two stars are separated by only a tiny fraction of a degree. When you block Alpha Centauri A with the coronagraph mask, Alpha Centauri B is still shining at full brightness just off to the side, adding its own glare to the image, its own diffraction patterns, its own interference. So now you have two overlapping systems of rings and spokes spreading across the same field of view, tangled together, each one making the other harder to clean up. This is the environment in which the team was trying to detect something extremely faint. Not just faint, extraordinarily faint. To tackle it, the team at the Space Telescope Science Institute developed a custom observation sequence specifically for this target. No standard template existed for observing something like Alpha Centauri with Webb. The geometry of the system, the brightness of both stars, the way they move across the sky together, all of it required a tailored approach that had never been done before. They designed a sequence of observations that captured the star at multiple orientations and positions, giving them reference images they could use to model the diffraction patterns and subtract them out. James Webb's mid-infrared instrument, MIRI, was the tool they used. MIRI observes in the mid-infrared range of the spectrum. That matters because planets don't just reflect starlight. They emit their own heat. And in the mid-infrared, that thermal emission becomes detectable in a way it simply isn't in visible light. A planet that would be completely lost in the glare of a star at optical wavelengths can show up as a distinct thermal source in the infrared. MIRI was built with a coronagraphic mode for exactly this kind of work. It has the mask, it has the sensitivity, and it operates at wavelengths where warm planets glow. The August 2024 observations took all of this and put it to work. The team pointed MIRI at Alpha Centauri A. They deployed the coronagraphic mask over the star. They ran their custom sequence. They collected the data, and then began the work of processing it. That processing is not simple. You take the raw images, which still contain all the diffraction artifacts even after the mask does its job. You use reference images, exposures taken with the telescope pointed at other stars in the same configuration, to build a model of what the instrument's optical signature looks like under these conditions. Then you subtract that model from your data. What you're trying to do is remove everything you understand, all the known patterns, all the predictable interference, and see what's left. What's left in principle is only the things that are actually there. Background galaxies, optical ghosts, and if you're lucky, planets. The team worked through those layers carefully. They accounted for Alpha Centauri B's contribution to the image. They modeled and removed the spoke patterns. They subtracted the ring structures. Round after round of analysis, each one pulling more of the known noise out of the picture. And something remained. It didn't look like a galaxy. It didn't match the profile of an artifact. It was a point source, compact and distinct, sitting in the cleaned image after everything else had been stripped away. Think about what that means. To show up after all of that subtraction, this object had to be real and had to be emitting actual mid-infrared light of its own. The brightness of that source compared to the brightness of Alpha Centauri A told the team something staggering. This object was more than 10,000 times fainter than the star. 10,000 times. Put it another way, if Alpha Centauri A were a floodlight on a stadium, this object would be a single firefly hovering somewhere in the stands. That's the scale of the difference between star and candidate planet. And Webb found the firefly. The separation between the detected object and Alpha Centauri A placed it at roughly 2 astronomical units from the star. 2 astronomical units. That's about twice the distance between Earth and our Sun, not in the freezing outer reaches of the system. not at a safe, distant remove where detection would be easier. Right in the neighborhood of the inner solar system, embedded in the region where rocky planets and gas giants can form and survive. What emerged from all that subtracted noise was something no telescope had ever clearly shown us before. Something sitting roughly twice as far from Alpha Centauri A as Earth sits from the Sun. What the team found orbiting Alpha Centauri A appears to be a gas giant, roughly the mass of Saturn. Think about that for a moment. Not Jupiter, not some bloated 10 times Jupiter monster orbiting far out in the cold. Saturn, the ringed planet, the one you can see in a backyard telescope on a clear night, the one whose rings stretch wide enough to swallow several Earths laid side by side. Saturn is about 95 times more massive than Earth. Its diameter is 9 times wider. It's enormous by any human scale. And yet, in planetary terms, Saturn is a middleweight, a gas giant, yes, but not the heavyweight class. That's what Webb found sitting around our nearest stellar neighbor. The candidate orbits Alpha Centauri A somewhere between 1 and 2 astronomical units out. 1 astronomical unit is the average distance from Earth to our Sun. So this world sits in a zone that, in our own solar system, would encompass Earth's orbit at the near end and stretch out past Mars at the far end. That's not the outer cold of the system. That's the inner neighborhood, warm territory. And the orbit doesn't appear to be a neat circle. The evidence points to something more stretched out, more elliptical, swinging closer to the star at certain points and pulling farther back at others. More on what that means shortly. But first, consider what kind of world this actually is. Saturn is a gas giant. There's no surface to stand on, no ground beneath your feet. You'd just fall inward through thickening layers of hydrogen and helium, the pressure climbing until the gas transitions to something more like liquid, and deeper still to something stranger and denser. The atmosphere churns with storms. Saturn has a storm near its north pole shaped like a hexagon, wider across than 4 Earths, that has been spinning continuously for as long as we've had instruments capable of observing it. The radiation belts around Saturn trap charged particles and accelerate them. The rings, those famous rings, are made of ice and rock, ranging from grains of dust to chunks the size of houses, all orbiting in a flat sheet. It's an alien environment by every measure, and what Webb found around Alpha Centauri A appears to belong to that same class of world. Now here's where this gets genuinely remarkable. Most of the planets we know about were never seen. Not directly. The vast majority of confirmed exoplanets were found through indirect detection methods. One of them is called the transit method. When a planet passes in front of its star from our perspective, it blocks a tiny fraction of the star's light. We measure that dimming. We measure how often it repeats. From that, we can deduce the planet's size and orbital period. Another method is called radial velocity. A planet's gravity tugs on its star as it orbits. That tug causes the star to wobble slightly toward and away from us. We detect that wobble through tiny shifts in the star's spectrum. From those shifts, we can estimate the planet's mass and orbit. These methods are indirect. You're inferring the planet from its fingerprints, not seeing it directly. Direct imaging is different. Direct imaging means you're actually detecting light from the planet itself, either light reflected from its star or heat the planet radiates on its own. You're capturing photons that came from the planet. That's extraordinarily hard. Stars are blinding. A star like Alpha Centauri A outshines any planet orbiting it by factors that are almost absurd. We're talking about a planet that's more than 10,000 times fainter than its star. Trying to see it is like trying to spot a firefly hovering a few feet from a searchlight while standing miles away. The searchlight doesn't just outshine the firefly. It floods the entire scene with so much light that the firefly simply ceases to be detectable. Getting around that requires blocking the star precisely enough that something 10,000 times dimmer can emerge from the background noise. That's what Webb did, and what it revealed would be historic under any circumstances. But the specific circumstances here push it further. Alpha Centauri A is a G-type main sequence star, a yellow dwarf, the same classification as our own sun, same temperature, same color, same basic stellar type, and the ages match as well. The Alpha Centauri system is roughly 5 billion years old. Our solar system is about 4.6 billion years old. So Alpha Centauri A is, within a rounding error, the same kind of star as our sun at the same stage of its life. No planet has ever been directly imaged around a star that matches the sun so precisely in both temperature and age. Not once. That's not a minor footnote. That's a genuine first. There's a cultural layer here worth pausing on. In the Avatar film series, a gas giant orbits Alpha Centauri A. The moon of that gas giant is Pandora, the world the story takes place on. When filmmakers were building that setting, they weren't just reaching for an exotic location. They were reaching for the nearest plausible analog to Earth they could find in real astronomy. And now, astronomers using the most advanced telescope in human history have found evidence of what may actually be a gas giant around Alpha Centauri A. The science fiction premise isn't confirmed science, but the distance between fiction and reality just collapsed in a way that feels genuinely strange. A Saturn-mass world around Alpha Centauri A, directly imaged, sitting at distances comparable to the inner planets in our own solar system, orbiting a star so similar to our sun that the comparison is almost uncomfortable. And around a world like that, there could be moons. Saturn has 146 of them. That detail matters enormously, but it belongs to a later part of this story. What matters right now is the simple fact of what just happened. For all the centuries humans have looked at that bright point of light in the southern sky, we had never seen anything orbiting it. No hint of another world. Just the star, blazing, silent, offering nothing. Then Webb looked, and something was there. Directly imaging a planet is one of the hardest things a telescope can do, and Webb had just done it next door. Then it was gone. In February 2025, the Webb team pointed MIRI back at Alpha Centauri A. They ran the same process, coronagraphic mask in place, blocking the star's glare, subtracting the light from Alpha Centauri B, cleaning up the diffraction rings. They looked for the object that had shown up so clearly 6 months earlier. Nothing. No signal. No faint point of light sitting 2 astronomical units out from the star. The candidate planet had vanished completely. They tried again in April 2025. Same result. Nothing. Think about what that means for a moment. The most powerful space telescope ever built using a custom observation sequence developed specifically for this target found something in August 2024 that it could not find again in 2 separate follow-up attempts. That is not a comfortable result. It is not the clean confirmation story anyone was hoping for. It is something far more unsettling because it leaves 2 possibilities on the table, and neither one of them is easy. The first possibility is that the August 2024 detection was wrong. Not wrong in the sense of sloppy science. The team was meticulous, the data reduction was careful, and the analysis went through multiple rounds of validation. But telescopes produce artifacts. Light bends around the edges of a coronagraphic mask in complex ways. Diffraction creates rings and spokes of residual brightness that look like real sources if they aren't subtracted perfectly. Background galaxies exist. A passing asteroid could leave a signal in a single exposure. Any of these things could have produced an apparent detection that wasn't actually a planet. If that's the explanation, it means one of the most celebrated early results from Webb's planetary science program was a false positive. That would be a sobering outcome. Webb is supposed to be the instrument that ends ambiguity, not creates it. The second possibility is stranger and, in some ways, more interesting. The planet is real. It was there in August. But between August 2024 and February 2025, it moved. Not disappeared, moved. It swung along its orbit and pulled too close to Alpha Centauri A to be seen. The star's glare swallowed it. Even Webb, with all its sensitivity, can't pull a planet out of the bright core of a stellar image when the planet is sitting directly in front of or behind the star from our vantage point. If the planet's orbit is sufficiently elongated and sufficiently tilted relative to our line of sight, it could have been visible at one point and then hidden at another, all within a span of a few months. This is what astronomers call an eccentric orbit. Not eccentric as in unusual or strange, though it may be both of those things. Eccentric in the technical sense, an orbit that isn't circular, an orbit shaped more like a stretched ellipse than a perfect ring. In a circular orbit, a planet maintains roughly the same distance from its star throughout its year. In an eccentric orbit, the planet swings in close and then pulls far back out, tracing a long oval path. The distance from the star changes dramatically depending on where in the orbit the planet is sitting at any given moment. The candidate around Alpha Centauri A appears to have been sitting near its farthest point from the star when Webb caught it in August 2024. That's roughly 2 astronomical units out, twice Earth's distance from the Sun. At that distance, it was just barely outside the edge of the coronagraphic mask, just barely far enough from the star's core brightness to be detectable. 6 months later, if its orbit brought it back in toward 1 astronomical unit or closer, it would have slipped behind the wall of light that no telescope can see through. The research team ran the numbers. They simulated thousands of possible orbits consistent with the August 2024 detection, different eccentricities, different tilts, different orbital periods. What they found was significant. In roughly half of all those simulated orbits, the planet would have moved too close to Alpha Centauri A by February 2025 for Webb to detect it. Half. That means the non-detection in February and April doesn't rule out the planet. It just means the geometry may have worked against them. If the planet exists and its orbit falls into that category, it would be invisible to Webb during those windows no matter how good the observation was. But here's what makes this genuinely tense. The other half of those simulated orbits would have kept the planet in a visible position. In those scenarios, a real planet should have shown up in February and April. It didn't. So either the orbit belongs to the half where the planet hid itself, or the planet was never there. The data cannot currently tell you which one is true. The computer models don't favor one outcome over the other strongly enough to settle it. There's also the question of orbital tilt. A planet's orbit doesn't have to lie flat relative to our line of sight. It can be inclined, angled toward us or away from us at various degrees. A tilted eccentric orbit can move a planet through a very wide range of apparent positions in the sky over the course of its year. Depending on how steeply the orbit is inclined, the planet could swing from a detectable separation to a completely hidden position quite rapidly. The team's modeling included inclined orbits, and they found that inclination made the disappearance easier to explain without abandoning the detection entirely. None of this resolves the problem. It just maps out the territory of the uncertainty. The August 2024 detection was real enough that the team published it. It matched a tentative earlier sighting from 2019. The position, the brightness, the separation from the star. All of it was consistent with a Saturn-mass gas giant in an orbit around Alpha Centauri A. But the follow-up observations came back empty. And science doesn't get to choose which data it believes. All of it counts. The detection counts. The non-detections count. The picture they paint together is genuinely unresolved. What the research team did not do is declare the planet confirmed. They also did not declare the detection a false alarm. What they said, carefully and precisely, is that the candidate remains a candidate. The orbital mechanics are consistent with the planet being real and temporarily hidden. But consistent with is not the same as proven. In science, those two phrases are separated by a very wide gap. The planet hadn't been ruled out, but it hadn't been proven either, and that distinction matters enormously. To understand why the planet might have disappeared, you have to think about what kind of orbit it might be following. Most people picture planetary orbits as circles. That's how they're usually drawn in textbooks. The planets go around the sun in tidy rings, evenly spaced, predictable. But that's not quite right. Real orbits are ellipses. Some are nearly circular, like Earth's. Earth's orbit varies only slightly between its closest and farthest points from the sun. The difference is small enough that we barely notice it in terms of temperature from season to season, but other orbits are stretched, pulled long and narrow. Think of a circle that someone grabbed at both ends and pulled apart. That shape is an ellipse, and some planets and comets follow paths that are dramatically elongated. A comet diving in from the outer solar system is a good example. It swings close to the sun, blazing bright for a few weeks, then retreats back into deep cold darkness for thousands of years. Same orbit, wildly different positions depending on when you look. The candidate planet around Alpha Centauri A may follow something like that. Not as extreme as a comet, but stretched enough to matter. At its closest approach to Alpha Centauri A, the planet sits roughly 1 astronomical unit out. 1 astronomical unit. That's the same distance Earth sits from our Sun. At its farthest point, it swings out to roughly 2 astronomical units. Twice Earth's distance. That's somewhere around Mars territory in our own solar system, maybe a little beyond. Think about what that swing means. The planet isn't just moving along a fixed ring, it's tracing an elongated loop. It comes in close, it moves back out. The time it spends at any given distance isn't uniform. Near the star, it moves fast. Far from the star, it slows down. That's just orbital mechanics. Kepler figured this out 400 years ago. Now think about what Webb can and can't see. The coronagraph blocks the star's direct glare, but there's still a zone close to the star where everything is washed out, masked, or overwhelmed by diffraction patterns. The planet was visible in August 2024 when it was near its farthest point from Alpha Centauri A. That's when it was at maximum separation, farthest from the glare, best position for detection. By February 2025, if the orbit is elliptical, the planet had moved. It was closer to the star, potentially back inside that blinded zone where no instrument can reach it. The planet didn't disappear from the universe, it disappeared from view. Those are very different things. So where did the ellipse come from? That's where Alpha Centauri B enters the picture. Alpha Centauri B is a real star, not a background object, not a distant companion. It orbits Alpha Centauri A at an average distance of roughly 11 astronomical units. For comparison, that's about the distance between our Sun and Saturn. It's close enough to be a dominant gravitational presence. Not close enough to strip away a planet's orbit entirely, but close enough to tug. Over millions of years, that gravitational influence works on nearby planets the way a slow, steady hand reshapes clay. It doesn't happen in a single orbit, it accumulates. Each pass around Alpha Centauri A, the planet feels a slightly different pull from B depending on where B is in its own orbit. The net effect over geological time is to stretch the orbit into an ellipse. This process has a name. Astronomers call it secular perturbation. It's well understood mathematically, and it's not theoretical. We see versions of it in our own solar system. Jupiter does this to smaller bodies throughout the solar system. Jupiter's gravity is so dominant that it has shaped the asteroid belt, cleared entire orbital zones, and flung comets inward toward the Sun across billions of years. There are asteroid families whose orbits have been slowly distorted by Jupiter's gravitational reach over millions of years. They started in more circular paths. Jupiter pulled them into ellipses. Some fell into the inner solar system. Some were ejected entirely. Alpha Centauri B is no Jupiter, but the principle is the same. A massive gravitational neighbor reshapes what lives nearby. Given enough time, even gentle forces add up to dramatic changes in orbital shape. The researchers modeled this. They ran simulations. They tested hundreds of possible orbits consistent with the August 2024 detection and asked which of those orbits would have hidden the planet from view in February and April 2025. The answer was roughly half. In about half of all plausible simulated orbits, the planet moved too close to Alpha Centauri A to be separated from the star's glare in the follow-up observations. Half. That's not a fringe outcome. That's not a desperate rescue of a failing theory. That's a legitimate, well-supported possibility. The non-detections in early 2025 don't rule out the planet. They're consistent with it having moved to an unfavorable position in its orbit. Think about that. We may have caught this planet at the single best moment in its entire orbital year to be seen. The one window where it was far enough from the star for Webb to pick it up. And then the window closed. The planet swung back in. The glare swallowed it again. We looked and found nothing, not because nothing was there, but because we were looking at the wrong phase of the orbit. It's like trying to spot a satellite in low Earth orbit with the naked eye. Sometimes the angle is perfect, and it blazes across the sky. 2 minutes later, it's gone. Not because it stopped existing, but because the geometry changed. This is why orbital mechanics matters. A circular orbit stays visible at roughly the same angular distance from the star throughout its year. An elliptical orbit is visible during part of the year and hidden during the rest. The more elliptical the orbit, the smaller that visible window becomes. And if Alpha Centauri B has been steadily stretching this planet's orbit over millions of years, the orbit may be quite elliptical by now. The next opportunity to catch the planet at maximum separation from Alpha Centauri A is projected for August 2026. If the orbit is real, that's when it should reappear. The planet wasn't necessarily gone. It may have simply swung back into the glare, hidden in plain sight around the nearest star we've ever watched. There's one more piece of evidence that makes this harder to dismiss. Back in 2019, years before Webb existed as an operational telescope, a team of astronomers was already hunting for planets around Alpha Centauri. They used the European Southern Observatory's Very Large Telescope in Chile. The instrument they developed for this specific purpose was called NEAR, New Earths in the Alpha Centauri region. That name alone tells you what they were hoping to find. The NEAR experiment was a collaboration between the ESO and Breakthrough Initiatives, the same organization behind the Breakthrough Starshot laser sail project. They modified the VLT's existing thermal infrared instrument with a new coronagraph and a special deformable mirror designed to suppress starlight. The whole system was built with one target in mind: Alpha Centauri A. They wanted to see what was there. What they found was tentative, a signal, a faint source in the mid-infrared, sitting at roughly 2 astronomical units from Alpha Centauri A. The team, led by astronomer Kevin Wagner, was careful about how they described it. They didn't call it a planet. They called it a candidate, a detection that couldn't be confirmed. There were too many possible explanations: a background object, an artifact of the instrument, noise in the data. A single observation by a single instrument doesn't prove anything. That's how science works. You see something once and you write it down carefully and you say, "This needs more investigation." The 2019 result was interesting. It wasn't proof. So it sat there for 5 years, a footnote, a maybe. Then Webb looked at the same star in August 2024. Different instrument entirely, different technology. Webb's MIRI operates in the mid-infrared same general wavelength range as the VLT observation, but with far greater sensitivity and from the stillness of space rather than through the turbulent atmosphere of Earth. The coronagraphic techniques are different, the data processing is different, the team analyzing the results is different, and when they cleaned up the image and subtracted the noise and pulled out the faint signal hiding underneath all that starlight, they found something sitting at roughly 2 astronomical units from Alpha Centauri A. Same location. 5 years later. Think about what that means from an investigator's standpoint. You're not looking at one data point anymore. You're looking at 2 data points, separated by 5 years, produced by 2 completely different instruments operated by different teams using different methods, pointing at the same star, and finding something in the same general region of space. The probability that both instruments independently generated the same artifact in the same location by coincidence is low. Not impossible, but low. That's not how random noise behaves. Random noise doesn't repeat itself across 5 years and 2 separate observatories. The position match is significant for another reason too. If this is a real planet following an elliptical orbit between roughly 1 and 2 astronomical units, then its position in space changes over time as it moves around the star. A real planet detected in 2019 would have moved. The 2024 detection should not be in exactly the same spot, and it isn't exactly. The positions are roughly consistent with what orbital mechanics would predict for a body following the kind of eccentric path the modeling suggests. That's a much more specific claim than simply saying 2 detections found something in the same general area. The detections are consistent with the same object in motion. That matters, but here's where the detective work gets complicated again. The February 2025 Webb observation found nothing. The April 2025 observation found nothing. So now you have 2 positive detections, 2019 and 2024, and 2 non-detections, early 2025. How do you weigh that? 4 data points, split evenly between finding something and finding nothing. This is the kind of situation that frustrates scientists and the public alike because it doesn't resolve cleanly into a yes or a no. The disappearance in 2025 could mean the 2019 and 2024 signals were both wrong. Or it could mean the planet was simply not where Webb could see it in early 2025, hidden behind the star's glare at a tight point in its orbit. Both explanations are consistent with the available data. What scientists do in situations like this is run the numbers. They build computer models of every possible orbit that would place the planet where it was seen in August 2024. Then they ask how many of those simulated orbits would also position the planet behind the star or too close to it for Webb to detect in February and April of 2025. The answer was roughly half. About half of all simulated orbits consistent with the August detection would have moved the planet out of view by early 2025. That doesn't prove the planet is there, but it means the non-detections don't prove it isn't there either. The data are genuinely ambiguous. The 2019 sighting adds weight to the scale on the side of real, not conclusive weight, just weight. A single VLT detection with a custom-built instrument in 2019 is shaky on its own. A Webb detection in 2024 with a completely different instrument is stronger but still uncertain. The combination of both 5 years apart in positions consistent with the same orbiting body is harder to explain away than either one alone. Astronomers say this openly. They're not claiming discovery. The paper describing the Webb observations uses the word candidate throughout. The researchers are measured. They lay out the evidence. They describe the uncertainty. They list the alternative explanations. And then they say that something at that location, at that brightness, appearing twice over 5 years, deserves serious follow-up. That's the honest scientific position, not certainty, not dismissal. Something in between. 2 instruments, 5 years apart, finding the same thing in the same place. That's not nothing, even if it's not proof. If this planet is real, it raises a question that planet formation theorists have been arguing about for decades. How does a gas giant form around a star that has a close companion pulling on everything nearby? That question isn't new, but the Alpha Centauri system makes it sharper than almost anywhere else in the sky. Let's start with how planets form at all. Every planet in our solar system began the same way. A giant cloud of gas and dust, left over from the formation of the sun, spread out into a flat, rotating disk. That disk is called a protoplanetary disk. Material inside it wasn't evenly distributed. Denser patches formed first. Gravity pulled nearby gas and dust toward those patches. The patches grew. Small clumps became larger clumps. Larger clumps became planetesimals, rocky bodies the size of mountains or small moons. Those planetesimals kept colliding, kept merging, kept growing. Over millions of years, that process built planets. It's called accretion. It's slow, grinding, incremental, and it requires the disk to be reasonably stable. That's the key word: stable. The process works when the disk is left alone long enough for material to accumulate without being flung apart. Disrupt the disk too much, and accretion stalls. Planetesimals that might have merged instead miss each other, scatter outward, or get dragged into the star. The building blocks of planets disperse before they can become anything substantial. Now introduce a second star. Alpha Centauri B orbits Alpha Centauri A at an average distance of roughly 11 astronomical units. That's about the same as the distance between the Sun and Saturn. These 2 stars have been circling each other for billions of years, and during the early life of the system, when Alpha Centauri A's protoplanetary disk was still forming, Alpha Centauri B was right there, pulling, tugging, stirring. The gravitational influence of a companion star doesn't just nudge a disk gently, it truncates it. Models of binary star systems consistently show that a disk around one star gets cut off at a fraction of the orbital separation between the 2 stars. For Alpha Centauri A, that means the disk may have been limited to roughly 3 astronomical units or less, maybe less than that. The outer edges of the disk would have been shredded by the tidal forces from B. Material there couldn't hold together. It was too disturbed. Think about what that does to planet formation. In our own solar system, the giant planets formed far from the sun. Jupiter formed beyond what astronomers call the snow line, the distance at which water freezes into ice. Beyond the snow line, solid material was more abundant. Ice added to the mass of planetesimals. Cores grew faster. Once a core reached roughly 10 Earth masses, its gravity became strong enough to pull in enormous amounts of gas from the surrounding disk in a process called runaway gas accretion. That's how you get a gas giant. You need a big enough solid core, you need enough gas in the disk, and you need enough time before the disk dissipates. All 3 of those requirements are harder to meet in a truncated disk. The disk around Alpha Centauri A was smaller. It had less material to work with at large distances, where giant planet formation is most efficient. The gravitational stirring from Alpha Centauri B would have increased the relative velocities of planetesimals in the outer disk, making collisions more destructive than constructive. Instead of merging, small bodies would have shattered each other apart. Building a solid core large enough to trigger runaway gas accretion would have taken far longer than usual, possibly too long before the disk disappeared entirely. So the conventional picture says, you probably can't build a gas giant around Alpha Centauri A. Not at 2 astronomical units. Not in a system that has Alpha Centauri B stirring things up from the outside. And yet something was detected at roughly that distance. There are a few ways to make sense of that. One possibility is that the planet didn't form where it was found. Gas giants in our own solar system didn't necessarily stay where they formed. Jupiter is thought to have migrated inward from its original position, pulled by its gravitational interaction with the disk and with Saturn. This is called planetary migration. A gas giant that formed farther out in the Alpha Centauri A disk, closer to the edge of B's influence but just outside it, might have had enough time to build a core and accumulate gas. Then, as the disk evolved, that planet could have migrated inward to the distance where Webb detected it. Migration doesn't solve every problem. A migrating planet still has to survive Alpha Centauri B's gravity as it moves. Its orbit could have been stretched into an ellipse rather than a circle. The eccentricity that astronomers believe this candidate has might actually be a signature of that gravitational history. A planet shaped and shoved by 2 competing gravitational fields for millions of years doesn't end up in a clean circular orbit. It ends up in an eccentric one. Another possibility is that our models of disk truncation are too aggressive. Observations of real binary systems show more diversity than theory predicts. Some disks around stars in binary systems are larger than models suggest they should be. Some persist longer. Planet formation is messy in practice. The neat theoretical picture of a sharply truncated disk may not capture everything that actually happens when gas and dust collapse in a system with 2 forming stars. There's also the question of when. The Alpha Centauri system is about 5.3 billion years old, somewhat older than our own sun. The planet formation process finished a long time ago. We're looking at the outcome of billions of years of dynamical evolution. A planet that formed under difficult conditions, migrated inward, and survived in an eccentric orbit for 5 billion years would be nearly indistinguishable from a planet that formed easily. We see the endpoint, not the process. What we don't see is a theoretical framework that comfortably explains a Saturn-mass world at 1 to 2 astronomical units around one member of a tight binary system. Current models don't predict it. Some simulations say it's possible under specific conditions, but those conditions are constrained and uncertain. The discovery doesn't fit neatly into what we expect. That's what makes it genuinely significant for planetary science, beyond the excitement of finding something close to home. Not just that a planet might exist around the nearest sun-like star, but that its existence in that particular system challenges the assumptions built into decades of planet formation research. The very existence of a gas giant there would mean our models of how planets form in binary systems need serious revision. Set aside the uncertainty for a moment and just think about what this world might actually be. We have a candidate, a gas giant roughly the mass of Saturn, orbiting a star nearly identical to our own sun. That's what the data suggests, and even without confirmation, that description alone is worth sitting with, because we know a tremendous amount about what a world like that looks like. We've had one parked in our solar system for billions of years. Saturn is not a world you can land on. There is no surface. You wouldn't fall toward the ground if you descended into Saturn's atmosphere, because there is no ground, not in any meaningful sense. You'd pass through clouds of ammonia ice and water ice, layer after layer, pressure building around you, the atmosphere growing thicker and hotter the deeper you went. Eventually, the hydrogen stops behaving like a gas. It starts behaving like a liquid. Keep going, and it transitions into something stranger still, a state called metallic hydrogen. where electrons flow freely through the material the way they do in copper wire. That's what's at the heart of Saturn. Not rock, not iron, just hydrogen, compressed beyond anything we experience in ordinary life, conducting electricity, generating a magnetic field that extends millions of miles into space. Think about that for a moment. The entire planet is made of the two lightest elements in the universe, hydrogen and helium, stacked in layers of increasing pressure until those elements stop behaving the way we expect. There's no surface to stand on, no ocean to sail across, nothing solid at all, just atmosphere all the way down. Now put that world around Alpha Centauri A. Alpha Centauri A is almost a twin of our Sun. Its surface temperature is roughly 10,000 degrees Fahrenheit, nearly identical to the Sun's 10,000 degrees. Its luminosity is a little higher, about 1.5 times the Sun's output. Its mass is about 1.1 times the Sun's mass. It's slightly larger, slightly brighter, slightly more energetic, but in all the ways that matter for a planet's environment. Alpha Centauri A looks a great deal like home. A planet sitting 1 to 2 astronomical units from Alpha Centauri A receives light that feels familiar. At 1 astronomical unit, the radiation environment would be close to what Earth experiences from the Sun, maybe a little more intense given the slightly higher luminosity. At 2 astronomical units, it would be cooler, something like what Mars receives, but warmer. The light itself would look almost the same to human eyes, slightly more yellow-white, warm and steady and relentless. So picture this gas giant, this Saturn-mass world hanging in that light, its upper clouds catching the glow of a sun that looks, from that distance, almost exactly like our own. Its atmosphere banded in deep ambers and pale yellows, laced with storm systems that have been turning for thousands of years. Radiation belts wrapped around the planet in invisible rings, charged particles spiraling along magnetic field lines. And somewhere in the distance, a companion star, Alpha Centauri B, a second point of light in the sky, bright enough to cast faint shadows at night. Webb detected this candidate in the infrared. That matters. Infrared is heat. Young gas giants retain heat from their formation, the slow gravitational collapse that ignited the fusion process in the planet's core, or in this case, just the heat of compression. Saturn still radiates more energy into space than it receives from the Sun. It's still cooling down from the event that created it. A Saturn-mass planet around Alpha Centauri A, if it's real, would likely be doing the same. The infrared brightness Webb observed would be the planet's own warmth leaking out into space, the leftover glow of its birth. That signal is faint. We said it before, 10,000 times fainter than Alpha Centauri A itself. And yet there it is, a warm, dark, enormous thing, drifting in the light of a familiar sun 4 light years away. But here's where it gets truly remarkable. Saturn has 146 known moons. 146. They range from tiny chunks of ice to worlds with their own geological history. Titan is the most extraordinary. It's larger than the planet Mercury. It has a thick nitrogen atmosphere, thicker than Earth's relative to the moon's gravity. It has weather, not water weather, methane weather. Methane rain falls from orange methane clouds onto methane lakes that sit on a surface of water ice as hard as granite. The Cassini mission landed a probe on Titan in 2005. The probe, called Huygens, sent back pictures of a flat, hazy landscape that looked in a disturbing way like a foggy riverbed, rounded pebbles of ice sitting in what appeared to be a dry drainage channel. A world that had never once been touched by sunlight strong enough to warm it past -290 degrees Fahrenheit. And yet, it had weather. It had rivers. It had lakes. It had an atmosphere complex enough to produce organic chemistry. Astrobiologists have been thinking about Titan for a long time. The chemistry happening in Titan's atmosphere, driven by ultraviolet light from the distant sun, produces complex organic molecules. Tholins, they're called. Dark, sticky compounds that settle on the surface and represent the building blocks that, on a warmer world with liquid water, might eventually lead to something more complex. Now imagine a moon-like Titan orbiting this candidate gas giant around Alpha Centauri A. The parent planet is roughly as massive as Saturn. There's no reason physically that such a planet couldn't host a similarly rich moon system. The same processes of gravitational capture and accretion that built Saturn's moons could operate around any gas giant in any star system. And a moon in that environment, orbiting a gas giant at 1 to 2 astronomical units from a sun-like star, would receive roughly Earth-like levels of stellar radiation. That changes everything. A Titan-like moon in that position would be warm enough for liquid water to exist if the conditions were right. The atmosphere would matter. The geology would matter. But the raw energy budget, the amount of light and warmth arriving from Alpha Centauri A every second, would not be the limiting factor the way it is for Titan in our own solar system. We are 4 light-years from that system. 4. Our galaxy is 100,000 light-years across. The most distant confirmed exoplanets lie thousands of light-years away. Planets we've found in other systems that might be habitable are hundreds of light-years away at minimum, places we could study in the abstract but never reach, never resolve, never examine in the kind of detail that would answer any real questions about life. Alpha Centauri is 4 light-years away. That's not close in any practical sense, we've established that. Getting there is essentially impossible with current technology. But on the scale of the galaxy, it is our backyard. It is the nearest thing there is. Any moon orbiting this candidate planet would be the nearest object outside our solar system that could plausibly, under the right conditions, harbor something. If something like Titan orbits this candidate planet, we're talking about the closest potentially habitable world humanity has ever had reason to consider, and we can almost reach out and touch it on a cosmic scale. To appreciate what Webb actually did here, you have to understand what it takes to find something 10,000 times fainter than the star it orbits. That number is worth sitting with. 10,000 times fainter. If you took the light from Alpha Centauri A and divided it into 10,000 equal pieces, the planet candidate is hiding somewhere in a single one of those pieces. Every previous telescope we've ever built would have drowned it completely. The star's light would simply swamp the signal. You'd never know anything was there. Webb gets around part of that problem by looking in infrared. That's the key. Most telescopes, including Hubble, observe primarily in visible light, the same wavelengths our eyes detect. Infrared is different. It's heat radiation. Everything with a temperature above absolute zero emits it, including planets. A gas giant orbiting at 1 to 2 astronomical units from its star absorbs stellar energy and radiates it back out as heat. In visible light, that planet is almost invisible against the blinding glare of a nearby star. In mid-infrared wavelengths, the contrast improves dramatically. The planet is still faint, but it's glowing in its own right. Webb's mid-infrared instrument, MIRI, was built specifically to detect that kind of thermal glow. It operates between roughly 5 and 28 microns, well into the infrared range where warm planets stand out more clearly against their stellar backgrounds. But MIRI alone isn't enough. A star like Alpha Centauri A is still extraordinarily bright, even in infrared. You need a way to block the star itself before you can see anything near it. That's where the coronagraph comes in. A coronagraph is, in its simplest form, a mask. It physically blocks the disk of the star at the focal plane of the instrument, preventing that light from ever reaching the detector. The idea dates back to a solar telescope built in 1930 to study the sun's outer atmosphere. Webb's version is more sophisticated. MIRI carries 4 coronagraphic masks designed for different wavelengths and different star sizes. You position the mask precisely over the target star. It blocks the direct stellar disk, and suddenly you can see the faint neighborhood around it. The problem is that masking a star doesn't make its light disappear entirely. Light bends around the edges of the mask. It diffracts. It creates rings, arcs, spoke-like patterns that spread across the image in concentric waves. The brighter the star, the worse those diffraction patterns are. Alpha Centauri A is one of the brightest stars in the sky. The patterns it creates around a coronagraphic mask are intense and complex. And that's before you account for Alpha Centauri B sitting right next door, pouring additional light into the same field of view, creating its own overlapping patterns. Cleaning all of that up requires software as much as optics. The team uses reference images, observations of other bright stars made under similar conditions, to model the known patterns the instrument produces. Then they subtract those models from the Alpha Centauri images. What's left, ideally, is the real structure of the system. Anything genuinely present in the space around the star that wasn't part of the instrumental artifacts. It's painstaking. Each layer of subtraction has to be done carefully because if you subtract too aggressively, you can erase real objects along with the noise. The candidate planet sits right at the edge of what this process can reliably recover. There's another layer to this. Alpha Centauri moves across the sky faster than almost any other star. It's close enough that its proper motion, its actual lateral movement through space, is measurable year to year. Standard coronagraphic observing sequences aren't built for targets that move that quickly. The team had to design a custom observing program from scratch. No template existed for this. They had to figure out how to track the star, position the mask correctly, schedule the observations to maximize their sensitivity to the region around Alpha Centauri A, and build in enough reference exposures to make the subtraction work. That custom sequence was the difference between getting usable data and getting nothing. Now think about the mirror. Webb's primary mirror is 6.5 meters in diameter. That's about 6.5 times wider than Hubble's 2.4-meter mirror. Surface area scales with the square of the radius. Webb collects roughly 7 times more light than Hubble in any given exposure. More collected light means fainter objects push above the detection threshold. A planet that would register as zero signal in a Hubble image might register as a faint but measurable point source in a Webb image. That's not a subtle improvement. 7 times more light is the difference between seeing and not seeing for objects at the very edge of detectability. Hubble has been looking at Alpha Centauri for decades. It resolved the 2 sun-like stars as separate points of light, which ground-based telescopes couldn't even do reliably. But Hubble couldn't find anything near either star. The planet candidate detected by Webb in August 2024 was simply beyond Hubble's reach. Not marginally beyond it, completely invisible. There was no combination of exposure time or processing technique that would have revealed it with Hubble's instruments because Hubble doesn't have MIRI, doesn't operate at mid-infrared wavelengths, and doesn't carry a coronagraph capable of suppressing a star as bright as Alpha Centauri A. What Webb did was combine infrared sensitivity, coronagraphic masking, a mirror nearly 3 times wider than anything previously in orbit, and a custom-designed observing sequence, all aimed at a problem that required every one of those elements simultaneously. Remove any one of them, and the detection goes away. The candidate object that emerged from the processed August 2024 data was more than 10,000 times fainter than the star it appeared to orbit. It showed up as a small excess of infrared light at a specific location, separated from Alpha Centauri A by roughly 2 astronomical units. Faint, but there. Consistent with the thermal emission expected from a gas giant at that distance from that star. The fact that any instrument could pull a signal like that out of so much noise at a distance of just over 4 light-years is a kind of miracle of engineering. The next chapter in this story has a date on it: August 2026. That's when orbital mechanics predict the candidate planet, if it actually exists, should be back in a position where Webb can see it again. The star's glare, the planet's elliptical path, the geometry of the whole system, all of it lines up again in August 2026 in a way that gives the telescope a clean window. Researchers have already mapped out the timing. They know when the viewing angle should be favorable. They're applying for telescope time right now to make the attempt. Think about what a successful detection in August 2026 would actually mean. You'd have 3 data points: a tentative signal from the Very Large Telescope in 2019, a clear detection from Webb in August 2024, and then a third sighting from Webb in August 2026 at a position consistent with the same object moving along the same orbit. 3 independent observations, years apart. 2 different instruments, same location in the sky. At that point, you're not dealing with noise or artifact or coincidence. At that point, you have a planet. That's how astronomy works. It's never one observation. It's never one instrument. It's layers. Each new measurement either confirms what came before or forces you to rethink it. The sun's mass was refined over centuries of better and better data. The distance to the nearest stars took decades of careful parallax measurements before anyone trusted the numbers. Every major discovery in astronomy follows the same pattern. One detection raises a question, a second detection sharpens the question, a third makes the question very hard to avoid answering. August 2026 is the third detection, or the non-detection that changes everything. But Webb won't be working alone by then. There's another telescope entering the picture, and it was built for exactly this kind of problem. The Nancy Grace Roman Space Telescope is scheduled to launch in late 2026, possibly as early as the fall. It's a different instrument from Webb in almost every way that matters for this specific problem. Webb has a massive 6.5-meter mirror. Roman's mirror is smaller, closer to 2.4 meters. On paper, that sounds like a step backward. Smaller mirror means fewer photons collected, which generally means less sensitivity to faint objects. But the mirror size isn't the whole story, not even close. Roman was built with a coronagraph unlike anything that has ever flown before. Webb's coronagraphic mode was designed as one capability among many. Roman's coronagraph was engineered from the ground up as a dedicated planet hunting instrument, optimized specifically for detecting planets around nearby bright stars, exactly like Alpha Centauri A. The engineering behind it is different in kind, not just degree. It's designed to suppress starlight with a precision that Webb's coronagraph wasn't built to match at these particular distances and wavelengths. The timing of Roman's launch matters enormously. If the planet is real and its orbit follows the predictions, Roman will arrive precisely when the viewing window opens. That coordination wasn't accidental. Astronomers have planned this convergence carefully for years. The 2 telescopes will observe the same region of sky in overlapping time frames, turning what might have been one telescope's best effort into a coordinated search using 2 fundamentally different detection methods. This represents the modern approach to solving astronomy's hardest problems. And there's something else. Roman operates in visible light. Webb sees in the infrared. Those aren't 2 ways of looking at the same thing. They're 2 completely different kinds of information. Infrared tells you about heat. When Webb detected that object around Alpha Centauri A, it was detecting thermal radiation, energy radiating off the planet's warm atmosphere. That infrared signal is how the team estimated the planet's mass and temperature. But infrared alone doesn't tell you how large the planet is in physical size. It doesn't tell you how much visible light the planet reflects. It doesn't tell you much about the planet's surface or upper atmosphere in ways that connect to habitability. Visible light does. A planet's reflectivity in visible wavelengths, astronomers call it albedo, tells you something about what the upper atmosphere is made of. Ice clouds reflect differently than methane haze. Ammonia reflects differently than water vapor. If you combine Webb's infrared data with Roman's visible light data, you start building a real picture of what you're looking at. Not just a heat signature, an actual world with physical properties you can measure. Think about how different those two pieces of information are. Infrared says something warm is there at this distance. Visible light says, this is how bright it is. This is what it's reflecting. This is what its clouds might be doing. Together they become a profile, a description, the beginning of an answer to the question of what kind of planet this actually is. That's why the combination matters so much. Roman can't see as faint as Webb can in infrared. Webb can't match Roman's coronagraphic precision in visible light. But together, pointed at the same target, they cover each other's blind spots. This is how astronomy has always made its biggest steps. Hubble saw things Palomar couldn't. Webb sees things Hubble couldn't. Roman will see things Webb can't. Not because each new telescope makes the previous one obsolete, but because each one adds a frequency, a wavelength, a precision that wasn't there before. The picture gets built one layer at a time. Alpha Centauri A is 4.3 light-years away. That makes it impossibly close in cosmic terms and still unreachably far in human ones. But right now, two of the most capable observatories ever built are being aimed at it in different wavelengths, with different instruments, at different times, all trying to answer the same question. Between Webb's infrared eye and Roman's visible light coronagraph, we may be standing on the edge of knowing, for the first time in human history, whether there is a world orbiting the nearest sun-like star. Proxima Centauri, the actual nearest star to Earth, has already given us something remarkable: confirmed planets. 3 of them. Proxima b was found first in 2016. It orbits inside what astronomers call the habitable zone, the range of distances from a star where liquid water could exist on a rocky surface. Then came Proxima c, a larger world farther out. Then Proxima d, a smaller candidate closer in. 3 planets around the nearest star to our solar system. That sounds extraordinary, and in one sense, it is. But here's what most people don't realize when they hear that. Proxima Centauri is not like our sun, not even close. It's a red dwarf. That's a star so small and so dim that it barely qualifies as a star by the standards we're used to. Proxima Centauri has a mass of about 1/8 the mass of our sun. Its surface temperature is roughly 5,400 degrees Fahrenheit, compared to the sun's 10,000. It puts out so little light that if you replaced our sun with Proxima Centauri, Earth would be plunged into permanent darkness. The sky would go black, the oceans would freeze. Life as we know it would end within weeks. To be in the habitable zone of a star that faint, a planet has to move in extremely close. Proxima b orbits its star at a distance of about 0.05 astronomical units. For comparison, Mercury, the innermost planet in our solar system, orbits the Sun at 0.39 astronomical units. Proxima b is roughly 8 times closer to its star than Mercury is to ours. It completes a full orbit in just 11 days. Think about what that means. At that distance, the planet is almost certainly tidally locked. One face permanently turned toward the star, the other face permanently turned away. One side baking in perpetual red light, the other side in permanent frozen night. A razor-thin zone around the terminator, the border between day and night, might be habitable. Maybe. The physics gets complicated fast. And then there are the flares. Red dwarfs are violent in ways our sun simply isn't. They're magnetically active. They produce intense ultraviolet and X-ray flares that can be far more powerful relative to their size than anything our sun generates. A major flare from Proxima Centauri can bathe an orbiting planet in radiation levels that would strip away an atmosphere over geological time. Proxima b has almost certainly been bombarded by thousands of these events. Whether it retained any atmosphere at all is genuinely unknown. Whether it has liquid water is unknown. Whether conditions there could support any form of life is unknown. These aren't small uncertainties, they're fundamental ones. This is the problem with red dwarf habitable zones. The zone exists on paper. The math says the temperature could be right, but the environment around a red dwarf is hostile in ways that go beyond simple temperature. Close-in orbits mean tidal locking. Tidal locking means extreme climate gradients. Intense flare activity means radiation bombardment. Any planet sitting in that zone earns the label in a narrow technical sense, and then faces a gauntlet of conditions that may make habitability impossible anyway. Now set that next to what a planet around Alpha Centauri A would experience. Alpha Centauri A is a G-type star, same classification as our Sun. Its surface temperature is almost identical, about 10,700 degrees Fahrenheit compared to the Sun's 10,000. Its luminosity is slightly higher than the Sun's, about 1.5 times as bright. Its mass is about 1.1 times the Sun's mass. It's 4.85 billion years old, roughly half a billion years older than our Sun. If you swapped our Sun for Alpha Centauri A, Earth's climate would barely change. The difference in incoming energy would be small. Life, if it existed here under our Sun, would likely continue without interruption. A planet in Alpha Centauri A's habitable zone would orbit at roughly 1 astronomical unit, same as Earth. It would take roughly a year to complete its orbit. It would receive roughly Earth-like amounts of starlight. It would not be tidally locked. At that distance, tidal forces from the star are weak enough to allow normal rotation. It would see a sun almost identical to ours rising and setting on a regular cycle. The flare environment would be completely different too. Alpha Centauri A does produce flares, but nothing like the violent outbursts of a red dwarf. A planet there would face a radiation environment broadly similar to what Earth experiences. The magnetosphere, if the planet had one, would handle it. So when astronomers talk about the candidate planet Webb detected around Alpha Centauri A, they're not just excited about finding another gas giant in another distant system. They're excited because Alpha Centauri A is the most sun-like star we can realistically study. Any planet there, or any moon orbiting that planet, exists in conditions far more analogous to our own situation than anything Proxima Centauri can offer. Proxima b gets the headlines. Nearest star, habitable zone, confirmed planet. The story writes itself, but confirmed doesn't mean habitable. The label is technical. The reality is a world bathed in flares, probably locked to its star, probably stripped of its atmosphere, circling a dim red ember at a distance closer than Mercury. The candidate around Alpha Centauri A is not even confirmed yet. It might still turn out to be an artifact, an error, a ghost in the data. But if it's real, and if it has moons, the way Saturn has moons, those moons would orbit a gas giant circling a star almost exactly like our Sun, at almost exactly the same distance Earth sits from ours. A world around Alpha Centauri A, if confirmed, would exist in a much gentler light, orbiting a true twin of our own Sun. Here's what's actually unsettling about all of this. Not the planet. The planet, if it's real, is extraordinary. A Saturn-mass world orbiting the nearest sun-like star in the sky. That would be one of the most remarkable discoveries in the history of astronomy. That part isn't disturbing. That part is wonderful. What's disturbing is everything surrounding it, the circumstances, the implications, the things this observation forces you to sit with if you think about it carefully enough. We have been watching Alpha Centauri for centuries. It's the brightest star system in the southern sky. Navigators used it, ancient cultures named it. Astronomers have pointed instruments at it for generations. It is the most observed, most studied, most discussed stellar neighbor we have. And in August of 2024, the most powerful telescope ever built looked at it and found something we had never seen before. Something sitting right there. 2 astronomical units out from Alpha Centauri A. Not hidden at the edge of some distant galaxy. Not buried behind clouds of interstellar dust. Right there, around the nearest sun-like star, in plain sight. Think about that. We didn't miss it because it was far away. We didn't miss it because the technology didn't exist to look. We missed it because the star itself was too bright. The thing we were staring at was also the thing blinding us to what orbited it. The answer was always there. We just couldn't see past the glare. And when we finally built something capable of blocking that glare, of masking the star and staring into the space around it, something emerged from the noise. Faint, 10,000 times fainter than Alpha Centauri A. But there. That's the first unsettling thing. The second one is worse. Webb found it. And then Webb looked again, twice, and couldn't find it. February 2025, April 2025, nothing. The same region of sky, the same instrument, the same star, and the object that had been there in August was gone. Now, there are explanations. Orbital mechanics can account for a disappearance like this. An eccentric orbit could have swung the planet back behind the star's glare. Computer models show that half of all plausible orbits consistent with the August detection would have made the planet invisible by February. That's a real possibility. It's not a desperate excuse. The math supports it. But here's what sits with you after you've heard all of that. The most powerful telescope ever built found something next door and then lost it. Not in a galaxy billions of light years away, not around some faint red dwarf at the edge of the catalog. Next door. 4 light years. And right now, we don't know if what we saw was real. We don't know if the light we detected in August was a planet, an artifact, a background object, something else entirely. We have a candidate. We have a match with a 2019 observation. We have orbital models that support a real detection, and we don't know. That's not a failure of science. That's just what science actually looks like. Uncertainty, incomplete data, a result that refuses to resolve cleanly in either direction. But it still sits oddly when you hold it up against the scale of the instrument that produced it. Webb cost $10 billion. It took 30 years to build. It operates 1 million miles from Earth in a permanent deep space orbit. It can detect an object 10,000 times fainter than the star it orbits. And it found something and lost it. And now we're waiting. There's a third thing. The models. For a long time, astronomers assumed that binary star systems were hostile to planet formation. 2 stars orbiting each other closely enough to share a gravitational neighborhood would disrupt the disk of gas and dust that planets form from. The material gets stirred. Planetesimals get scattered. A full-scale world shouldn't be able to grow there. That was the theoretical expectation, not a fringe view. The mainstream understanding of how planet formation works in close binary systems. And now something that looks like a gas giant has turned up around Alpha Centauri A, 1/2 of a close binary pair, at an orbital distance of 1 to 2 astronomical units. Either the models are missing something important, or the planet formed somewhere else and migrated inward. Or the detection isn't real. All 3 of those options are significant. None of them are comfortable. The universe keeps doing this. We build models based on the physics we understand. We test them, refine them, confirm them in dozens of different systems. The models get better. They predict things correctly. And then something turns up that sits just outside what they said was possible, and the whole structure has to be re-examined. Not thrown out, adjusted, extended, pushed into territory it hadn't covered before. This is how science works, and it's how it's always worked. But there's something specific about it happening here, at this address, around this particular star. Alpha Centauri A is the nearest Sun-like star to Earth. If we're ever going to understand what kinds of worlds exist around stars like our own, this is where that understanding begins. It's the best case, the clearest signal, the shortest distance, and it's already showing us that our expectations don't hold. Already, before we've confirmed a single planet, the nearest Sun-like system is behaving in ways that don't fit neatly into what we thought we knew. That's what's disturbing. Not danger, not threat. Just the quiet recognition that the universe, as always, is under no obligation to behave the way we expect. Let's think about what it would actually mean to go there, not to observe it, not to point a telescope at it and collect photons that left a star 4 years ago. Actually go there, board something, leave Earth, and arrive at Alpha Centauri the way you arrive at any destination, by crossing the space in between. The distance is 4.3 light years. That number gets thrown around a lot and it sounds almost manageable. 4.3. Not millions, not billions, just 4.3. But a light year is the distance light travels in a full year. Light moves at 186,000 miles per second. In 1 second, it circles the entire Earth 7.5 times. In 8 minutes, it crosses the distance from the Sun to Earth. In 1 year, it travels about 5.9 trillion miles. Multiply that by 4.3. The distance to Alpha Centauri is roughly 25 trillion miles. 25 trillion miles separates us from our nearest neighbor. Think about what that means in practical terms. Among all spacecraft humanity has ever constructed, the Parker Solar Probe ranks as the swiftest. At its peak, it moves at around 430,000 miles per hour. That's fast enough to travel from New York to Los Angeles in about 20 seconds. It's the fastest thing we've ever launched. Point it at Alpha Centauri. How long does it take to arrive? About 6,300 years. 6,300 years. When the Parker Solar Probe finally coasted into the Alpha Centauri system, if it were aimed that direction, which it isn't, the ancient Egyptians wouldn't have built the pyramids yet by the time it launched. Human civilization, as we understand it, would need to begin, rise, fall, and rise again multiple times before it arrived. The probe would reach Alpha Centauri somewhere around the year 8,300 AD, assuming it held together, assuming no one turned it off, assuming the mission continued across a span of time longer than all of recorded history. And the Parker Solar Probe is the fastest thing we've ever made. Voyager 1 is a useful comparison. It launched in 1977. It's been moving through space for over 47 years. It's now the most distant human-made object in existence, about 15 billion miles from Earth. That sounds like an enormous distance. It is an enormous distance. But 15 billion miles is roughly 0.0026 light years. Alpha Centauri is 4.3 light years away. Voyager 1 has been traveling for nearly 5 decades and hasn't covered 0.1% of a single light year. If Voyager 1 were aimed at Alpha Centauri, again, it isn't, it would arrive in approximately 73,000 years. The species that launched it might not exist in a recognizable form by then. These numbers are not designed to impress you. They're designed to make you feel something. And what they should make you feel is the full weight of what we're actually talking about when we say Alpha Centauri is close. There is one serious proposal that aims to close this gap. It's called breakthrough starshot. The idea is audacious. Engineers and physicists have proposed building a spacecraft the size of a postage stamp, weighing about 20 grams, equipped with a tiny camera and communication array. The plan is to push it with a massive ground-based laser array, an enormous bank of lasers focusing their combined output on a reflective sail attached to the craft. The laser pushes the sail. The sail accelerates. In theory, the spacecraft reaches about 20% of the speed of light. At that speed, it would reach Alpha Centauri in roughly 20 years. 20 years is something humans can actually plan for. But think about what 20% the speed of light means for a 20-gram piece of hardware sailing through interstellar space. At that velocity, even a single grain of dust becomes a high-energy projectile. Interstellar space isn't empty. There are hydrogen atoms, microscopic particles, traces of material scattered between the stars. At 20% of light speed, each collision carries enormous kinetic energy. The spacecraft would need shielding capable of surviving a continuous barrage of particle impacts across 25 trillion miles. The sail itself would need to withstand the initial laser burst, gigawatts of focused energy, without burning apart. The communication signal it sends back, by the time it crosses 4.3 light-years, would be extraordinarily faint. And by the time it arrived, the scientists who proposed the mission would likely be dead. This is the most optimistic scenario we've designed. A postage stamp, 20 grams. No human being, no ability to stop or orbit or land. A flyby lasting minutes, photographing Alpha Centauri at 20% of light speed and then vanishing into the dark on the other side. That's the best plan we have. No one alive today will see what it finds. The person who might eventually read data from a breakthrough starshot probe at Alpha Centauri hasn't been born yet. The technology to build the laser array doesn't fully exist yet. The funding hasn't materialized. The mission hasn't launched. And even if everything went perfectly, even if a probe launched tomorrow and arrived in 20 years, the signal confirming its arrival would take another 4.3 years to reach us. Closer to 25 years, minimum, from launch to first data. That's what close looks like on an interstellar scale. We live on a pale blue dot in a quiet arm of the Milky Way, and our nearest neighbor, the system right next door, the one we've named, studied, and dreamed about for generations, requires civilization spanning timescales to reach with our fastest hardware. Everything we know about Alpha Centauri, we've learned by collecting light. Light that already made the journey. Light that left those stars years ago and arrived at our mirrors and sensors and detectors, carrying compressed information about what's out there. James Webb didn't go to Alpha Centauri. It sat at a distance of 4.3 light-years and read the light. And in that light, it found something that might be a world we cannot visit, cannot land on, cannot touch. A world we can only watch if we're patient enough, with instruments sensitive enough to detect something 10,000 times fainter than the star it orbits. Alpha Centauri is the closest thing in the universe to next door, and it is still incomprehensibly far away. Alpha Centauri A and B are older than the Sun, not by a little, by roughly 1 billion years. The Sun formed about 4.6 billion years ago from a collapsing cloud of gas and dust. Alpha Centauri A and B formed around 5.3 to 6 billion years ago. That gap is hard to hold in your mind. 1 billion years is longer than the entire history of complex animal life on Earth. It is longer than the time between the first fish and right now. It is not a rounding error. It is an incomprehensible stretch of time during which entire civilizations could have risen and collapsed. Stars could have lived full lives and died, and evolution could have run its course in ways we can barely imagine. But to understand what that age difference actually means, You have to go back further, further than Alpha Centauri, further than any star we can see tonight. You have to go back to the very beginning of the cycle. When the universe was young, it was almost entirely hydrogen and helium. No carbon, no oxygen, no iron, no calcium. None of the elements that make up a rocky planet. None of the elements that make up a living thing. The first stars burned through their hydrogen fuel and died, and when the massive ones collapsed and exploded as supernovae, they scattered newly forged elements into the surrounding gas. Carbon, oxygen, silicon, the heavier stuff. That enriched gas eventually collapsed again under gravity, forming new stars and the disks of material around them. New planets condensed from that debris. The same cycle happened again and again. Each generation of stars left behind elements the next generation could use. Alpha Centauri A and B formed from that enriched material, but they formed earlier than the Sun, which means the stars that seeded their formation, the ones that lived and exploded and scattered their contents into space, those stars died and were gone before our solar system even began to condense. The heavy elements sitting inside any planets around Alpha Centauri A were forged in stellar cores that no longer exist, cores that burned out before Earth had any mass to speak of. Think about what that means for life. Life, as far as we know, requires carbon. It requires oxygen. It requires nitrogen, phosphorus, iron, and dozens of other elements that only exist because stars died to make them. Every atom in your body was built inside a star. The calcium in your bones, the iron in your blood, the carbon in every molecule of every cell. All of it was forged under enormous pressure and temperature inside a stellar interior, then scattered across space when that star ended. You are, in the most literal physical sense, made of dead stars. That is not a metaphor, it is chemistry. The same process happened around Alpha Centauri. The elements were there, the conditions were there, and they had a head start. 1 billion years is an almost absurd advantage. Life on Earth took roughly 4 billion years to get from single-celled organisms to something capable of building a telescope. That timeline included 5 mass extinctions, hundreds of millions of years during which nothing more complex than algae existed, and enormous stretches of time where evolution was grinding forward in ways that left no obvious trace. 4 billion years of unbroken biological history, and here we are. That's what it took. If life formed around Alpha Centauri on a similar timeline, it had 1 billion extra years. Not a little more time to refine a few adaptations. An entire additional span as long as the history of complex animal life on Earth. Whatever that time might have produced is something we genuinely cannot picture. We have no frame of reference for what 1 billion extra years of evolution looks like, because we are the product of our own timeline, nothing more. Now, we don't know that life ever formed there. We don't know that the candidate planet Webb detected has moons. We don't know whether rocky planets exist around Alpha Centauri A at all. Everything in that direction is uncertain right now. But the age of those stars is not uncertain. That's measured. 5.3 to 6 billion years old. Older than the Sun, older than Earth, older than every fossil ever found. The cosmic cycle doesn't care about any of that. Gas collapses, stars ignite, stars age and swell and scatter their contents. New gas clouds form, new stars condense, new planets form from the wreckage of old ones. It has been running on this schedule since the universe cooled enough for atoms to exist. Alpha Centauri A and B are simply further along in that cycle than we are. They've had more time to accumulate heavier elements, more time for any orbiting worlds to cool and stabilize, and more time for whatever chemistry those worlds might support to develop in whatever direction it wanted to go. We spent the last section thinking about the distance. 4 light years, the impossibility of crossing it, the centuries it would take at any speed we've ever achieved. But distance isn't the only thing separating us from Alpha Centauri. Time is too. 1 billion years of it. If life ever took hold around Alpha Centauri, it has had 1 billion years more than us to figure out what it is. Most of the planets we've found were never actually seen. Think about that for a moment. We've confirmed over 5,000 exoplanets, 5,000 worlds orbiting other stars, and the overwhelming majority of them were detected as shadows and wobbles. A planet passes in front of its star, and for a few hours the star dims slightly. That's a transit. Astronomers measure the dip in brightness, calculate the planet's size from how much light it blocks, and infer its orbital period from how often the dip repeats. Or a planet's gravity tugs on its star as it orbits, and the star rocks back and forth just slightly. That's radial velocity. The star's spectrum shifts toward blue as it moves toward us, then back toward red as it moves away. From that wobble, astronomers can estimate the planet's mass and orbital period. Both methods work. They've been enormously productive. But here's what they don't give you. They don't give you a picture. You're inferring the planet's existence from its effect on the star. You're not seeing the planet itself. It's like detecting a car in a dark parking lot by watching the motion of a leaf blowing near it. You can make reasonable conclusions, but you haven't seen the car. Direct imaging is different. Direct imaging means you are actually collecting light from the planet. Photons that left the planet's surface or atmosphere and traveled across space and landed on your detector. That's the real thing. That's the actual object. And when you have photons directly from a planet, you can do something extraordinary. You can spread that light into a spectrum. You can see which wavelengths were absorbed and which came through. You can read the chemical fingerprints in the light itself. Water vapor absorbs at specific wavelengths. Carbon dioxide absorbs at specific wavelengths. Methane, ozone, oxygen, all of them leave marks in a spectrum that no other process produces in exactly the same way. This is how we would recognize life from 4 light years away, not by hearing a signal or seeing a city, by reading the chemistry of an atmosphere and finding combinations of molecules that couldn't coexist without biology constantly replenishing them. Oxygen and methane together, for instance. Oxygen destroys methane. If you find both in the same atmosphere, something is producing them continuously. Something like life. But until now, direct imaging has been locked out of the most important category of planets, the ones that matter most for this question. The directly imaged planets we have found are almost all young, massive, and very far from their stars, dozens of astronomical units out, sometimes hundreds. These are worlds recently formed, still glowing with the heat of their own creation, bright enough in infrared to stand out against the darkness far from their host star's glare. They're impressive discoveries, but they're not the kinds of worlds where we expect life. They're not sun-like stars. They're not Earth-like distances. No telescope before Webb has directly imaged a planet sitting close to a sun-like star. Close meaning within a few astronomical units. Close meaning the kind of distance where liquid water is possible. Close meaning the kind of orbit where a rocky world could, in principle, exist. That category has been completely invisible to us. Not because the planets aren't there, because they're buried in the blinding light of their stars, and we've never had the instruments to reach them. The Alpha Centauri candidate changes the boundary of what's possible. If confirmed, it would be the first planet ever directly imaged at roughly 1 to 2 astronomical units from a star that matches our own sun in temperature and age. That combination has never existed before in the confirmed catalog. Not once. The closest we've come are distant planets around younger stars. This would be something genuinely new. And the significance goes beyond this single detection. What it proves, or what it begins to prove, is that Webb's coronagraphic instruments can reach into the inner regions of nearby star systems and pull out signals from planets. That capability is the foundation for everything that comes next. Once you can image a gas giant at Earth-like distances, you've demonstrated that the technique works. You've shown that the optical suppression is good enough. You've shown that the data analysis can separate a real planetary signal from the noise of diffraction rings and stellar artifacts. That's the baseline, the stepping stone. The next step is smaller planets. Harder to see, obviously. A Neptune-sized world reflects less light and emits less heat than a Saturn-sized one. A super-Earth is harder still. A true Earth analog at 1 astronomical unit from a sun-like star is, with current technology, still beyond reach. But the path runs through exactly this kind of observation. You build the methods, you refine the coronagraphs, you develop better algorithms for subtracting stellar residuals. Each generation of instruments inherits the techniques developed by the last one. The Nancy Grace Roman Space Telescope carries a coronagraph specifically designed to push further into this territory. Roman won't have Webb's light-gathering power, but its coronagraph was engineered from scratch for exactly this problem, finding planets close to nearby bright stars. Visible light data from Roman would complement Webb's infrared detections. Infrared tells you about heat and temperature. Visible light tells you about reflectivity and atmospheric scattering. Together, the two instruments would give you a more complete portrait of a planet than either could produce alone. Instrument by instrument, measurement by measurement, the picture gets sharper. This is how astronomy has always moved. Brahe measured the planets more precisely than anyone before him, and Kepler used those measurements to find the laws governing orbital motion. Newton used Kepler's laws to derive gravity. Hubble used better telescopes to show that galaxies were receding. Every new capability unlocks a question that was previously unanswerable. Webb's ability to detect a planet 10,000 times fainter than its host star, at a distance of 4 light-years, sitting inside the orbital region where rocky worlds might exist. That is a new capability. It belongs in that lineage. Direct imaging of a planet at Earth-like distance from a sun-like star would open a door that has never been opened before. There's a question underneath all of this that nobody says out loud very often because it sounds too large. It sits beneath every Webb observation request, every coronagraph calibration, every orbital simulation the research team runs. Nobody writes it in the abstract of a scientific paper, but it's there. Are we alone in the universe? That's the engine. That's what all of this is actually about. Think about what that means in practical terms. Researchers had to develop a custom observation sequence just to look at Alpha Centauri A. No standard template existed. They applied for time on the most oversubscribed telescope ever built, knowing that every hour of Webb time is competed for by hundreds of teams studying everything from the early universe to dying stars. They won that time. They built new tools to use it. They planned follow-up observations in February 2025, April 2025, and they're already thinking about August 2026. That's years of effort, telescope time, and computing resources poured into one star system. The reason isn't purely the orbital mechanics or the infrared photometry. The reason is that Alpha Centauri A is a G-type main sequence star, almost identical in temperature and age to our own sun, sitting just over 4 light-years away. It is the single best candidate in the sky for finding a planetary system we could actually study in meaningful detail. Most exoplanets are forever out of reach. They orbit stars hundreds or thousands of light-years away. We can detect them. We can estimate their mass and radius. But studying them in depth, reading their atmospheres, measuring their chemistry, That's essentially impossible at those distances. Alpha Centauri is different. 4 light-years is still an incomprehensible distance by human standards. But in telescope terms, it's our backyard. And that proximity changes everything. Here's what characterizing a planet actually means. When astronomers talk about characterizing an exoplanet, they're talking about spectroscopy. You take the light that passes through a planet's atmosphere or reflects off it, and you break that light apart by wavelength. Different molecules absorb different wavelengths. Oxygen leaves a fingerprint. Water vapor leaves a fingerprint. Methane, carbon dioxide, ozone, each one has a distinct chemical signature written into the spectrum. You read the spectrum, you read the atmosphere. That's the goal. Not just finding a planet, but reading what it's made of. The reason that matters is chemistry. A rocky planet with oxygen and methane in its atmosphere at the same time is deeply unusual. Those two gases react with each other. They destroy each other. In a purely geological atmosphere, they can't coexist for long. The only known process that can continuously replenish both simultaneously is biology. Living things. That chemical imbalance, that signature of constant replenishment, is what scientists call a biosignature. It doesn't prove life, but it's the kind of evidence that would be impossible to ignore. We can't do that with the current candidate around Alpha Centauri A. It appears to be a gas giant Saturn class, and a gas giant's atmosphere isn't where you're looking for biology. But here's the roadmap. A candidate gas giant is step 1. Confirm the gas giant. Study it. Understand the architecture of the system. Are there other planets? How are the orbits arranged? Is there a region stable enough, at the right distance from the star, for a smaller rocky world to exist? The James Webb Space Telescope is finding the large objects first because large objects are easier to detect. The instruments that come after Webb will push the sensitivity further. Each generation of telescope looks a little deeper, a little closer in, at a little smaller object. A century sounds like a long time. It isn't in the context of this question. 100 years ago, we didn't know other galaxies existed. We didn't know the universe was expanding. We didn't have a single confirmed exoplanet. A century from now, with instruments we can't yet build using physics we haven't yet applied, the atmospheric spectrum of a rocky planet orbiting Alpha Centauri A might be a standard observational target. It might be something an astronomer requests the way astronomers today request a spectrum of a nearby star. Not a miracle, just science, advanced far enough. That's the ARC, gas giant candidate in 2024. Confirmation maybe in 2026. Further characterization of the system over the following decades. And somewhere in that line, a clearer picture of what else might be there. It won't be fast. It won't be simple. But the proximity of Alpha Centauri makes it the one place where that entire progression is plausible within a human timescale. The teams behind these observations understand this. That's why they built new observing sequences. That's why they're watching the calendar for August 2026. That's why the Nancy Grace Roman Space Telescope's coronagraph was designed with systems like Alpha Centauri explicitly in mind. Every technical choice, every instrument upgrade, every scheduled observation traces back to the same underlying logic. The nearest sun-like star is where the question becomes answerable. Not today. Maybe not for generations, but answerable. That's more than we can say for anywhere else in the sky. The question is whether we are alone, and Alpha Centauri is the closest place we will ever be able to seriously look. We started tonight with the idea that our nearest stellar neighbor was finally seen clearly for the first time, and what was found there was disturbing. Not disturbing the way a threat is disturbing. Not dangerous, not alarming, disturbing the way a deep question is disturbing, when you realize you've been looking at something your entire life and never actually seen it. Alpha Centauri has been in the sky forever. Ancient astronomers watched it. Every civilization in the southern hemisphere grew up under it. We named it, we mapped it, we pointed our best instruments at it for generations. And in August of 2024, James Webb looked at Alpha Centauri A with its infrared eye and its coronagraphic mask, blocked the star's blinding glare, stripped away the noise and the artifacts and the diffraction rings, and found something sitting there roughly twice as far from that star as Earth sits from the sun. Something 10,000 times fainter than the star itself. Something no telescope had ever clearly shown us before, and then it was gone. That's the part that stays with you. Not the discovery exactly, the disappearance. The fact that the most powerful telescope humanity has ever built found something next door. And then, in February 2025, and again in April 2025, couldn't find it again. It might be real. The orbital modeling says it could be real. The 2019 sighting from the Very Large Telescope says it might be real. But we don't know. And the not knowing is the whole thing. Think about what that means. 4.3 light years, our closest neighbor, the place we've been dreaming about since before we had the mathematics to describe what a star actually was, and we still don't know what's there. We caught a glimpse of something, and the universe pulled it back behind the curtain before we could get a good look. There are researchers planning for August 2026. There's a telescope called Roman being prepared for launch with a coronagraph built specifically for this problem. There are people who have dedicated years of their careers to figuring out what is or isn't orbiting Alpha Centauri A. That is not nothing. That is humans doing what humans do, which is refuse to accept that a question is unanswerable just because it's hard. And that's the thing worth holding on to at the end of all of this. Not the candidate planet, not the Saturn-mass estimate or the infrared brightness or the eccentric orbit. The remarkable part is that we looked, that someone built an instrument capable of detecting something 10,000 times fainter than a nearby star, that someone else developed a custom observation sequence just for this target because no standard template existed for a problem this difficult, that we are small enough to stand on one pale world and large enough, in some other sense, to point a mirror at a star 4.3 light years away and ask what's orbiting it. If you find yourself thinking about questions like that, about what's out there, about how far the universe actually goes and what might be living somewhere in it, consider subscribing. We cover these stories the way they deserve to be covered, which is slowly, carefully, and with the full weight of what they actually mean. Alpha Centauri will be there tonight. It will be there next August when Webb looks again. Whatever is or isn't orbiting it has been there for billions of years, long before any instrument existed to detect it, long before any mind existed to wonder about it. The stars are patient, and we are slowly learning to see.